So here we generalize the previous example with the following theorem. So this theorem tells us that if vector v sub 1, vector v sub 2, all the way up to vector v sub p are elements of a vector space V, then the span of these vectors is a subspace of vector space V. So before we get started here, if you have not had a chance to watch the previous example, please make sure that you do, as I'm going to go much more quickly through this proof here. We looked in more detail in the last case. So here is our proof. We're going to let vector v sub 1 all the way up to vector v sub p be vectors in our vector space V. And again, the goal here, we want to show that H defined by the span of all of these vectors v1 up to v sub p is a subspace of vector space V. Right, so we know that in order to show that this is a vector, a subspace of the vector space, we need to show that those three properties hold true. So case 1, we need to show that the 0 vector is in the span of these three vectors, or these p vectors. So to show that the 0 vector is in H, we simply rewrite the 0 vector as a linear combination of the vectors. So I have 0 times vector v sub 1, 0 times vector v sub 2, all the way up to 0 times vector v sub p. And since the span is the collection of all possible linear combinations, we know that the 0 vector is in H, which is defined by the span of all these vectors. So we have the 0 vector is in H. Next, we want to show that H is closed under addition. And so let's give ourselves a little bit more room. So I'm going to let vector u and vector v be two vectors in H such that vector u is defined as scalar c sub 1 times vector v1 plus scalar c sub 2 times vector v sub 2 all the way up to scalar c sub p times vector vp, and vector v is equal to, we'll say, d sub 1 times vector v1 plus d sub 2 times vector v sub 2, all the way up to scalar d sub p times vector v sub p. And we should make a little love note here to ourselves that the set of all these c values, c sub 1 to c sub p, are scalars. And the set of all these d values, d sub 1 all the way up to d sub p, are also scalars. And to show that this H is closed under addition, we take the sum. So I have vector u plus vector v, which we are able to rewrite as c sub 1 times d sub 1 times vector v sub 1 plus c sub 2 plus d sub 2 times vector v sub 2 plus all the way up to c sub p plus d sub p times vector v sub p, which shows us, or which is a linear combination of these vectors, and therefore is an element of H, which is the span. So therefore, vector u plus vector v is in the span of these vectors, because the span is the collection of all possible linear combinations. And that last vector should be p. And again, if you have not had a chance to watch the previous example, please do so that you can see what we just did in more detail. Last but not least, show that H defined by the span of these vectors is closed under scalar multiplication. And this is that third and final property here that we need. So I'm going to let vector u be some vector in H, and I'm going to be a little lazy here and say the same u as above. And we will let C be any scalar a little heart's desire. And so to show that our vector space, to show that H is closed under scalar multiplication, we take the scalar multiple. So I have scalar C times vector u, which we will be able to rewrite as C times C sub 1 times vector v sub 1 plus the scalar C times C sub 2 times vector v sub 2, and we continue all the way up to C times scalar C sub p multiplied by vector v sub p. And so since we have attained a linear combination here, we know that it's going to be an element of the span. So we can say, therefore, scalar C times vector scalar C times vector u is an element of H, which is the span of all of these vectors. And our third and final property has shown to be true, and so we're able to make the final conclusion. Since all three of these conditions are met, the span of the set of these vectors v sub 1, v sub 2, all the way up to v sub p, is a subspace of V. And there we have it.